Hi, and welcome to the second episode in this series where I'm building a synthesizer. And in this episode is going to sort of be a standalone tutorial about how you can build a basic audio module or synthesizer from a Teensy microcontroller and a DAC. So we're going to start with a lot of theory in the beginning, but if you just want to build the thing, you're going to need these parts, and then you can skip to a later part in the video where I will actually build it. But before we do that, we're going to do a lot of theory about how digital audio works. Okay, so here's the problem. We have a bunch of binary data. There's some magical process, and we want to turn that into a continuous analog signal which we can hear. So in order to do that, we need to essentially, we're going to represent our continuous wave with a series of discrete samples, okay? And each sample is just going to be a single number that represents the height of the wave at that point. So at regular intervals, we take these samples, which is represented by these blue dots. It can turn the wave into a list of discrete numbers, right? So in this example, it's -4, then the next sample is 0, 4, 7, 6, 3, and so on. So we've taken this continuous signal and we've turned it into a series of numbers. So the first thing to think about when you're sampling is the sampling frequency, which is essentially the rate at which you take samples. As we increase the number of samples per second, the accuracy of our digital audio is greater, and it better approximates the continuous wave. Here we have a more crude approximation, and then it gets better as we go down. The second constraint is the bit depth. Essentially, computers don't have infinite memory, right? And so if you want to store a number in the computer, you have to use a certain number of binary digits, which are called bits, and that number is fixed per sample. So essentially, you can kind of see on this example here, the samples always have to snap to the grid points, right? So on one half, we're using a finer grid, which allows us to more accurately measure the wave, and on the other side, we use a less fine grid, which would correspond to a lower bit depth. And you can kind of see that we have to approximate at some points. It doesn't quite snap onto the grid. So kind of in general, the higher the sample rate, the better the quality, and the higher the bit depth, i.e. the number of bits per sample, the better the quality. So does that mean that we should just crank these numbers as high as they'll go? Well, to answer that question, we should actually measure how these things affect the quality of the wave in a more scientific way. So sampling frequency will actually determine the range of frequencies that our audio can actually play. So if you take a piece of audio and you break it down into its component frequencies, this is what it would look like. And you can see that at a certain point, it just cuts out, and no frequencies higher than this point can be represented in our audio signal. And this limit here is known as the Nyquist frequency. The maximum audio you can represent is going to be half of the sampling frequency. So for example, if you have 32 kilohertz sampling, then you can only represent a frequency up to 16 kilohertz. Bit depth basically introduces random errors, because if you're sampling a wave, which is this red thing, you can see that we either have to snap to the grid line above or the grid line below. And essentially what this means is that half the time you're going to be overshooting, half the time you're undershooting. So you can kind of model it as random noise. And if you do the maths, at 12 bits, your signal to noise ratio is 74 decibels. And at 16 bits, it's 98 decibels. And if you know anything about decibels, these are actually really essentially inaudible. So what that means is that we should probably try and choose numbers which are sensible and going to produce good audio, but we don't need to max these numbers out just for no reason. So I've chosen 44 kilohertz as the sampling frequency, which means that our Nyquist limit is going to be at 22 kilohertz. And that's well above human hearing range, so going higher than this is unnecessary. And like I said, with 16-bit audio, you're getting a noise floor of 98 decibels, or negative 98 decibels. And that's basically inaudible, and it's much better than any analog system such as vinyl or cassette tapes. So going beyond these is essentially unnecessary, and some audio synthesizers like to advertise that they have 32-bit audio or whatever, and most of that is just sort of marketing rubbish. You don't actually ever need to go beyond these two limits. So there's a few myths about digital audio. The first myth is that the audio that's outputted by a DAC would look like this stair-step pattern, and that's not true. That's kind of never true, and the reality is that the DAC will smooth out the samples into a continuous analog wave. The second myth is that digital audio, especially digital synthesizers, are somehow lower quality than analog, and that's completely not true. And in a lot of ways, digital is going to be much better sounding than analog because it's more precise. So for example, if you want to output a pure sine wave, a digital synthesizer will be much better at that than an analog synthesizer, which introduces distortion, which can get out of tune, and in a lot of ways is imprecise. So how do you use an external DAC? Because the Teensy microcontroller doesn't have an inbuilt DAC, so we need to somehow send our samples to an external DAC. And the way you do that is with the I2S protocol, which is a sort of standard protocol for sending audio between integrated circuits. So the signal is broken into three parts. You first have a serial clock wire, which is essentially keeping a regular pulse, and it's kind of like a metronome. It's telling the other components when the bits are going to be sent. The second one is the word select. The word select essentially is telling the DAC which channel we're sending, whether it's the left or the right channel. And then the last channel is actually where we're going to send our binary data, which corresponds to our samples. Remember that the samples are just a long list of numbers, and those numbers can be transmitted in binary, which is what's sent here. Okay, one last thing we have to understand with digital audio is the DMA. So if you'll allow me, I'm going to tell you a bit of a strange story, and hopefully this should explain what a DMA is. So imagine that you have just inherited a number factory, and at this number factory you have a desk, and on the other side you have a telegraph machine, and that telegraph machine can transmit to the headquarters, which I'll represent here with Gordon Ramsay. Okay, so your job at the number factory is to create 32,000 fresh numbers out of these calculations, and once you've calculated all of those numbers, you need to then send them to HQ, which is Gordon Ramsay, and you should never be late. You should always meet your quota. You need to create exactly 32,000 fresh numbers every hour. But the good news is you have one employee, and his name is Albert Einstein. So Albert Einstein is a very diligent worker. He's good at calculating numbers, and he can operate a telegraph machine. So let's look at Albert Einstein's day as he's working at the number factory. So he'll spend about half an hour here calculating some numbers at his desk, and then after that he needs to move over to the other side of the factory and transmit the numbers that he's calculated through the telegraph machine. But there's a problem. Gordon Ramsay's not happy because you're not hitting your quota. And the problem is that despite how good Albert Einstein is, he's spending a lot of time transmitting numbers on the telegraph machine when he could be calculating, right? So he can't do both at the same time, and he's wasting a lot of time here when his talents are really best spent at the desk. So the first idea you might have as manager of the number factory is to hire a second Albert Einstein. He could operate the telegraph machine while the other Albert Einstein is calculating numbers. But the problem with this is that Einstein demands a very high salary, and so hiring them two together, you wouldn't be able to afford that. So instead, your idea is, what if we just hire a monkey? Because operating a telegraph machine is so easy, a monkey could do it, and we could pay them peanuts, literally. So let's see how this goes. We've hired a monkey. So now Albert Einstein's going to work on his numbers, and then he's going to have a blackboard here where he writes all of them down. He's going to pass the blackboard to the monkey, and now the monkey is going to transmit them to HQ. But there's a problem. If you're careful, you might have noticed we haven't actually increased efficiency at all here. And the problem is that while the monkey is, tapping things away on the telegraph machine, Einstein has no access to the blackboard, so he can't write down any of his calculations. So he has to spend time just doing nothing. And equally, while Einstein's writing down calculations on the blackboard, the monkey is just sort of sitting there doing nothing. So you haven't actually increased the efficiency of the number factory. So here's the idea. We're going to break the blackboard into two pieces. And now Einstein can work on one side of the blackboard, the monkey can work on the other side of the blackboard, and then once they're done, they just swap over the sides and continue. And so essentially, they can always be doing things. Einstein's always going to be writing on one half, the monkey's going to be transmitting on the other half. So both of them are always working 100% of the time, and now we've maximized efficiency. And all of this only cost us a few peanuts that we have to pay the monkey. So if you follow this weird story, you should now understand what a DMA actually is. DMA stands for direct memory access, and essentially the analogy is that the DMA is the monkey, right? Albert Einstein is the CPU. The CPU is very good at calculating numbers, right? The blackboard is our buffer, which is sort of a list of numbers where we store all of our samples. And of course, Gordon Ramsay, or HQ, is our DAC, which we're sending the audio to. Okay, so in real life terms, what does this all mean? So the CPU is going to be writing to this buffer of samples, right? Remember that our wave is just going to be represented as a list of numbers. So it'll write on one half, and then the DMA will be transmitting the other half. And then whenever the DMA reaches the end of its half, it's going to tell the CPU, hey, I've reached the end of this. And so then they're going to swap over like they did in the number factory. And essentially the DMA is sort of a very dumb computer, which we can add to our microcontroller. And for very little cost, we get to really dramatically increase the efficiency of our program, right? Let's summarize all of this and build our entire audio pipeline. So first, the CPU is going to write things to our audio buffer, and then the DMA is going to read things from the buffer. And the things it's writing are the samples, which we talked about in the first half. Then the DMA is going to transmit with I2S, which I talked about as well, and that goes to our DAC, and then our DAC outputs the audio. So that's all we need to know. Let's start actually building this thing. Okay, so what I have here is the Teensy board on one side and the DAC module on the other side. So the first thing I'm going to do here is just connect the two power rails to each other. Next, I'm going to take these wires and use the pins on the Teensy, which output regulated power. So this one outputs 3.3 volts. So we're going to hook up the 3.3 side to the plus and then the ground to the minus. So once you've done that, these rails will now be powered with 3.3 volts, and so we can use them to power the DAC module, which has a V in pin, which stands for voltage in, and a ground pin. So we're going to hook those up now. So now our DAC module is going to be powered by the Teensy. So now once it's powered, we need to hook up the three lines that consist of the I2S protocol. So the first line we're going to hook up is the data line, and the data line comes from pin 7, which is specified in the pin out sheet, where they show all of the audio pins in yellow. So now pin 7 goes to the data in, or DIN pin. Next up, we're going to put our B clock pin, which comes out of pin 21. Lastly, we need to hook up our word select, although in the documentation they seem to have called it LR select. So, but it's the same thing. So that's going to be pin 20. Pin 20. Okay, so that's our DAC hooked up. Lastly, I'm just going to hook up some buttons here, and those are going to be used just for testing. Later on, of course, our keyboard is the thing that's going to be controlling the synth, but just to test it, I want to put some buttons down. The buttons will go straight to ground, which essentially the pins are going to be held high by the microcontroller, and then when we press the button, it'll short the pin to ground, and that will force the pin low. So as you can see here, each button is now going to ground, and so now we can hook the other side of the button to the pins. So I'm just going to hook up to pins 1, 2, and 3. So now when you press the button, this pin will be shorted to ground, and you push this one, it will be shorted to ground. And we can use the software to detect when that happens. And that's it. So that's the whole sort of basic synth. You can see there's an audio jack here which we can plug into, and we can hear our sound. So what I have here is the board we just made. And so first you just need to connect it to the computer with the USB cable. And then secondly, I have here an audio interface, so I can connect the output here, the headphone jack, to my computer. Now lastly, I have on the computer, I can record everything that's coming in. So right now, if we just look at this wave, you'll see that what's coming in from the device is a pure sine wave, which shows that it's working. And I'll show you how to get this sine wave in just a second. So in order to get started with programming the thing, I've written here a template which you can find on my GitHub. I'll link this in the description, but for now what I'm going to do is just going to copy this and download the project. So here I'm going to git clone it, and I've got the project downloaded here. Now if you don't have Git, you can always just download a zip file of the code. So once we have the code downloaded, we can head over into Visual Studio Code, and you'll need the Platform IO extension installed. And once you have that installed, you can open the folder. So here's the folder that we just downloaded. We can select that, and it will open the project in Platform IO. So once you have the project open here, you can hit build down in the corner, and hopefully it should say success. Now you can upload the project, and if you have your Teensy plugged in with the USB, you should be able to hear a simple sine wave coming out of your DAC. It should sound like this. So I'm just going to start modifying this code a little bit, but before we do that, I'm just going to take you on a little tour around the code. So here's our main file, which contains our top level code. So when the code starts, it will be in here. As you can see, it calls this I2S begin function, which essentially just sets up our DMA in the hardware to transmit I2S to our DAC. I'm not going to go through all of this, but the main important thing is that we're going to specify which buffer that we want to transmit, which is this guy. And this is where we're going to be writing our samples. So I said that we'll be using 16-bit samples, but that means that each element of this array has to be 32 bits because we're transmitting left and right audio, so together they add up to 32 bits. So in here is where we have to write our samples, and then we also specify the size of it using these flags here. Lastly, we set an interrupt for the DMA, which means that once the DMA has transmitted half of the buffer, it will call this function that we set called onDMATransmit. From here, we detect which half of the buffer has been transmitted, and then based on that we call this generate wave function, and that function is going to tell the CPU to fill in the other half of the buffer. So this is the main meat of our program, and this is what's generating the samples. So if you want to add your own synth engine, essentially you wouldn't really touch any of this code, but you would be modifying this to generate a more interesting wave. Right now though, all that we're doing is accumulating a variable and then calculating a sine wave based off of that variable and then writing it out into our buffer. And here you can see we write into the buffer twice because we're writing for the left and right channels. So let's try and modify this to create a more interesting sound and also take input from our buttons. So you can see here that there's a frequency variable and a volume variable. The frequency variable just controls how often this accumulator will reset, meaning that the wave will change frequency if this value is higher. Then we also have a volume variable, and all we're doing there is timesing our sine wave by this volume variable, so that if it's 1, that's full volume, and if it's 0, that's silence. So in order to get input from our buttons, all we have to do is set the pin modes here. So we're going to set button 1 to an input pin mode, and we have to use the pull up pin mode because the way we've wired them means that when the button is pressed, it's gone to ground, but when it's unpressed, the pin is essentially floating. And if you don't specify pull up, that means that the value you get out of the pin is random. But if you specify pull up, that means that the pin will default to 1 when it's not connected to anything. That means that when we press the buttons, the pins will be pulled low. So we can read that in our loop function, which gets run continuously by doing button 1 equals digital read pin 1, and we have to check if that's low. Remember that when the button's pressed, the pin will be pulled low, and when the button is unpressed, the default will be 1, which is high. So it's kind of backwards from what you might expect. Based on what these buttons then read as, we can set different frequencies into our wave generation, right? So we've got a global variable here called gfrec, and I'm just going to set this to 440 if the button 1 is pressed. So now we have 3 different notes that we can play using our buttons. Lastly, if none of the buttons are pressed, we probably want to set the volume to 0. And then in order to set the volume back to 1, once you've pressed the buttons, we can just do that here. Okay, let's upload this and see what that sounds like. Okay, great. So not the most exciting synth, but you can see how we can build stuff from here. So maybe one of the problems is that the sound is a bit flat. There's no envelope to the sound. It just sort of turns on and then immediately turns off. So in order to add a bit of envelope, what we can do is create a float, which we'll call our volume target, and we'll set that to 0. And now, instead of directly setting the volume, what we'll do is we'll just set the volume target. And then when we set the volume, what we're going to do is just interpolate the volume target with what we want it to be. So we can use linear interpolation here. So we're going to set this to 0.01. So essentially, every update we will set it to mostly the value of the volume, but then we also introduce a little bit of the target into the volume. So eventually the volume will drift towards the target. So let's see what that sounds like. So that sounds a little bit more interesting, but I think one of the problems is that the volume doesn't have a very good attack to it. So what we can do is that when you press a button, maybe we'll just set the volume to 1 immediately, and then we'll only do this interpolation thing when you let go of the button. So that's starting to sound a bit more interesting. Maybe it sounds a little bit like a marimba. But what if we wanted to change the characteristic of the sound? Well, in our wave generation function, we're just using this sine here, but maybe we could change that into a sawtooth wave. So in order to do a sawtooth wave, all we would need to do is write a new function which generates a sawtooth wave from a given input. So we're going to take an input from 0 to 1, and we're going to use some formulas to turn that into a sawtooth wave. So the formula is pretty simple. All we need to do is, if it's less than half, we times it by 2. Otherwise, we times it by 2 and minus 2. In order to get that formula, all you have to do is play around on Desmos, and you can kind of see the sawtooth wave here. So now in our function, we can just replace the sine with that, and we don't have to multiply by 2 pi. And now we should get a nice sawtooth wave. Okay, that looks like it's it for this episode. I hope you learned a few things. I would like to invite you to see the code blog if you want to look at more details, which will be in the description. So next time we're going to be working on connecting the front end to the back end. We worked on the front end in the first episode, and the back end is what we've just made here. We're also going to try connecting a screen, and we're going to try and create the first sort of prototypes of our synth engine. So I hope to see you then, and thanks for watching.